As Andy mentioned, my name is Roger Pincombe. I'm a lead software engineer at Capital One, and I'm here to give you a brief overview of machine learning. Try and give you a practical overview so you understand the basics of what it is and how to use it in your design work. A bit about my background. I am creator of allthepeople.net, so I originally got into this because of the privacy aspect. That's a system I built that goes all over the internet and pulls your personal information, uses some machine learning to connect you across different services. It's kind of scary, but you should check it out. Anyway, I'm on Twitter at OKGoDoIt. So first, what is machine learning? You've heard a lot of buzz in the news. Robots are taking over all our jobs. But what does that actually mean? How does it work in practice? So I want to make a distinction between two different types of AI. We have strong AI. This is artificial consciousness, the stuff of sci-fi movies. The idea that you can make something that's basically human. You can tell it, hey, Siri, go make a website for me, and it knows what that means, and it understands in a human level or a greater than human level. That is not something that exists in the world. Maybe it'll exist someday, but it is not a thing yet. So when we talk about machine learning, we're talking about the other kind of AI. We're talking about narrow AI. And that's basically just math functions that are optimized to solve problems. So it doesn't have an understanding of a topic. But what you do is you use a certain algorithm, and I'll go over some of the different types of machine learning algorithms and what kind of problems they solve. But then you plug in the data that you use in your real-world scenario, and it can come up and figure out things like, oh, this is a picture of a dog. Now, before I get into the different kinds of machine learning, I want to make very clear you don't need to be a math expert to use any of this. There's basically two different strains of applying machine learning. You can be a research scientist. So Google has the Google Brain team. Facebook has the Facebook AI research team. There's lots of academic research. This is the kind of stuff that requires crazy advanced math, linear algebra. You're going to be doing a lot of derivatives. The kind of thing that where all the really interesting stuff is being discovered. But really, I want you to think about machine learning at this point, is it's at this point where you don't even need to know that. You just need to know how to use the tools. So for example, when I was in high school, I learned PHP. I was a PHP script kiddie. I made websites. I didn't know compiler design. I didn't know assembly programming, but I was still able to make websites using this higher level concept of PHP. So that's kind of where we are with machine learning today. You can use tools like TensorFlow, or Azure Machine Learning, or Amazon and Google have services as well. You can even use higher level services that you don't need to know any machine learning. You just send them an image and they'll tell you what's in it. So you can really kind of get at this at whatever layer is interesting to you and whatever layer you're comfortable with. So I want to go over a few of the different types of machine learning and what they're used for. And then I won't go too much into details about how exactly they work, but I want to give you a brief overview of the different types so when you're faced with a problem you want to solve, you know kind of which route to go down. First, I'm going to start with basic regression, or basic regression, supervised learning. So let me start with just use the example of you creating an e-commerce website to sell books. And you want to know what should the price of the book be to increase the sales the most. Now here's an example. This is a real life thing that came off Amazon a couple years ago. There's this book about, a really obscure book about fly genetics. And how much do you think this book is worth? You're closer back there. So there's actually, this book was sold by two sellers who both used algorithms that automatically came up with a price based on the average price in the market. And as you can see, they think this book is worth about $1.7 million. So one of the things I want to make sure to be clear about machine learning algorithms is they are not intelligent. They are just solving math equations. And if you give them the wrong math equations to solve, they will do stupid things. So for this example, it's going to be a little bit of math, but I'm going to keep it really simple, and I promise there's no more math for the rest of the presentation. But let's say we have a few different prices we've priced our book at. Maybe we did it for a week each, and we saw how many people bought it at $10, $20, $40, and $5. And we want some sort of system that, given a price, will tell us how many sales we can expect. Now, I've oversimplified this a bit, so take it with a grain of salt. But let's go ahead and put those prices on a graph here, or on a chart. So on our x-axis, we have the price. starting at 0 and going up to $50. And then on the y-axis, we have our purchases. So as we change the price, our independent variable, we have resulting purchases. And as you can see, there's less purchases the more you raise the price. If we go ahead and put a line through that, again, very simple, not exactly real world, but you'll get the basic idea. We put a line through that. Now we have a general idea of the trend, of the fact that as the price goes up, the sales go down. So if we want to ask a question like, how many sales can we expect if we price our book at $30? It's really simple. We just look on the x-axis, we see where it crosses, or we look at $30, we see where that crosses the line, and we see, it's about 26 purchases we can expect if we price our book at $30. So again, very basic. This is high school, or this is middle school algebra, basically. I'm going to refresh your memory a little bit. We have y equals mx plus b. That's the value, which is the number of purchases, is m, which is the slope of the line, times x, which is the price of the book, plus b, which is some constant that offsets it. And in this simple example, we come up with a slope of negative 0.8 plus 50. Again, it's fake numbers, but the important things to note here are that with these two numbers, the negative 0.8 and the positive 50, we now have parameters that we can pass into this equation. So given a price, we feed it into this machine learning black box, scary mumbo jumbo, but really all it is running this simple equation that tells us we can expect 34 sales. So you might look at the y equals mx plus b as the architecture, as the general shape of the algorithm. So again, this is oversimplified. It's called a linear model. We're just putting a line through it. And it only has these two parameters here. We've got the negative 0.8 and the 50. And in that case, that describes our data. Now, you can imagine if we had much more complex data. For example, we have the size of a buy button and the color and the number of reviews shown. Then the number of parameters we'll need to accurately describe that would increase. So that's where you get this issue of big data, and where you need a lot of examples in big data to actually properly figure out what those parameters are. In fact, in the real world, you get hundreds, thousands, tens of thousands of parameters in order to get accurate deep learning, machine learning models. So again, this is supervised learning. You can increase the number of, increase the type of input, the number of parameters. You need more data to figure out an actual pattern in there. The supervised learning is you know the inputs and you know what outputs you expect. So just in summary, supervised learning or regression analysis you could answer the question of how many ebooks could we sell at this price? So we're selling books, what price should we price it at? And it probably wouldn't be a simple linear model. It might be more of a quadratic model, but it would be basically we have data points and we just want to understand how we can interpolate them. Now I want to move on to unsupervised learning. So if supervised learning is where you know the answer, unsupervised learning is where you're just trying to interpret the data in some more abstract way. So for example, clustering is one of the more common uses of unsupervised learning. Let's say you have an e-commerce site. You probably have some sort of market segment analysis. You know that certain different types of people buy products from your site. Maybe the people in different income brackets or people that have different needs, and you might market to them differently. You might price things for them differently. In non-e-commerce situations, you might think of these as user studies. You have your example users and what they want out of your app. So with unsupervised learning, you might put in a bunch of data, for example, gender, income, states. You might have the technical data, what browser they use, where they came from, what kind of device they use. And as a human, you might intuitively say, okay, well, maybe there's some different groups here. But with unsupervised learning, you basically run it through. I'm not going to get into the details, but let's say a k-means algorithm or some other clustering algorithm where it might separate it into groups that have some sort of abstract concept in common. Now, I don't want to go too much in the details here, but let's just say that we were trying to interpret this, that maybe the first group, those look like high earners who may or may not be tech savvy. We see someone using Internet Explorer there. Maybe the second group is someone who's a mid-range earner. They're more tech savvy. Maybe they're a little conservative. We could read into this as much as we want. The idea is with more data, it would be more meaningful grouping. But this is more or less the idea of unsupervised learning is you're trying to figure out some structure from the data. You're trying to figure out some kind of more abstract information. So that could help us answer questions like who are our customers, what are our product segments, things like that. Okay. Next is the big one. This is the one that you guys have all heard about a lot because there's been a lot of really cool advancement happening in the past decade or so, and that's convolutional neural networks. Now, convolutional neural networks deal with things like understanding images. So you give the computer a picture of a dog, it knows that's a dog. You give it a picture of a person, it knows it's a person. You give it a picture of that, and it's confused. Uh, so again, the idea with convolutional neural networks is they help you recognize things that are in two-dimensional or spatial images. And this might be simple image recognition, but also you can do all sorts of interesting things. Here's a company called Cape Analytics. I actually talked with them a little over a month ago, and they're using satellite data to analyze the roofs of houses. So what they do is they actually partner with insurance companies, and they help estimate the price of your roof and if there's been any damage to it recently. So you can think after a major natural disaster, they might be able to go through and get updated satellite imagery, tell your insurance provider that, hey, your roof has major problems, and here's an estimate just from machine learning of how much it might cost. Now, it might not be perfect, but it's a great first pass, and it's a good way to keep the insurance companies or whoever else in the loop. Maybe you have a house in Florida and you only live there half the year, you didn't even know that your roof caved in. So some really interesting real-world scenarios there, and I'm going to get into how this can be used in medical a bit later in the talk. But I want to give you a brief overview of how this works. Now, this is going to be fairly high level, but where it mostly comes down to with convolutional neural networks is you have hierarchies of how things relate to each other. So in this example, we're going to talk about computers recognizing faces. And I'm going to show 3 layers, or 3 different levels in a convolutional neural network that analyzes faces. So the lowest level you'll see here on the left is actually not recognizing faces at all. It's recognizing things like dots and edges and kind of very simple concepts. And then as you get one layer up, it starts to understand things like, oh, if there's a dot with another dot, that might be an eye. Or if there's this triangle in a certain orientation, maybe that's a nose. And then as you go another layer up, you go through a little more abstraction. It might understand that if you have 2 of these things called eyes next to each other up on top of this thing called a nose, that maybe that's actually a face. And it's not quite that simple, obviously, but as you train this with more and more images, it starts to learn what goes into making up the overall idea of a face and not just the pixels that go into it. And this is pretty interesting because then you can have a picture of a face that's turned to the side, or maybe one of the eyes is occluded, and you can't actually see the whole face, but it can still understand based on the fact that there's enough relative information there that it looks like a face. How's the microphone, by the way? Can you guys hear me all right? Okay. Okay, here we go. What? Oh, hey there. You guys got it? You can hear it? Awesome. So that's kind of a high level of how convolutional neural networks work. They're used largely in images, and one of the places they're used most right now in real-world situation is for classifying user-submitted images as not safe for work or not. So Yahoo's actually done a lot of work with creating a filter that works really well. It's open source. You can download it. There's also paid APIs from Google and Microsoft and Amazon. You can feed it images. It'll tell you how likely it is to be an adult image. So if you're running a site that supports user-generated content and someone puts in this image of someone working not safely, it can tell you that it's not safe for work. Or this, they don't look like they're working very safe either. So safety first. So again, convolutional neural networks deal with spatial data, which generally means photos. And in the e-commerce book selling example, you might be able to say something like, is the cover of this book graphically inappropriate? Is this adult content? Now I want to move into something called generative networks. So you can imagine that if a computer can understand what's in images, what happens if we run that backwards? So let's see what a computer thinks a dog looks like. It's vaguely dog-like. So you might have seen this. A couple years ago, Google came out with this really cool system called Google Deep Dream. And what they basically did is they took their existing systems they'd used to recognize images, and they more or less ran them in reverse. So remember when I talked about how it understands that a face is a collection of eyes and mouth and whatnot? So here we're looking at a face, and we're seeing something that it thinks, okay, well, maybe that's a face, and so let's put some eyes in it. And actually, it looks like that might be the outline for a face. Let's put another face inside of it. So it's clearly not perfect. We as humans can understand, we can look at that and say, that is not a real picture. That's pretty trippy. So if we want accurate images, what if we train a computer to be able to figure out if the images are real or computer generated? So this is the idea of a generative adversarial network. So there are actually 2 separate networks. We have one that's the discriminator network, and we feed that one a bunch of pictures, a bunch of real pictures of our subject matter, let's say real pictures of dogs, and we also feed it the output from the generative network. And so its job is to say with some degree of confidence, this is a real picture or this is a generated picture. Now, what's really cool about generative adversarial networks is they kind of teach each other. They work in tandem. So you start off with a discriminator that doesn't work very well. It's really bad at telling the difference. And you start off with a generative network that doesn't generate very good images. And as the discriminator gets better at determining if this is a real image or not, the generative network has to get better to keep up. It has to try and trick the discriminator. So as one gets better, it forces the other to get better. And it's a little hard to balance it in practice, but if you get it right, they basically end up teaching each other. There's some cool things you can imagine doing if you can generate images. So for example, here's something where we've trained a generative adversarial network to generate pictures of birds based on descriptions. And we have a few descriptions of birds. For example, this small bird has a pink breast and crown and black primaries and secondaries. And we have 6 images that were actually generated by a computer algorithm. Now, they're not perfect. They're kind of blurry. They look mostly bird-like. But it's pretty surprising that it took the text and it came up with those images. And you can imagine this is an area of active research that's getting better and better over time. So maybe in a few years you might be able to describe a website and it'll pop up a mock-up, who knows. But I do want to tell you something that is pretty exciting that works right now, that is an actual practical use of this. So something called Pix-to-Pix. This recently came out, I think, earlier this year, maybe the tail end of last year. And the idea is to train network to take an input of some sort of rough image. In this case, it almost looks like MS Paint of a building facade. So the front of a building, where we're basically having a basic diagram. We want to process it into a photorealistic preview. So let's say you're an architect or something, and you want to see what would happen if I put a balcony right here. So I've gone ahead, and I actually did this yesterday. This is live output. I went ahead and just drew a rectangle to put a balcony there. And I clicked the process button, and you can see that image looks pretty much the same, except it's got a balcony in the lower right. Now, let me replay that again, because it's a little hard to see the difference, because the photo does look fairly photorealistic. There's before, and there's after. Now, the lighting is due to the fact that the adversarial networks sometimes don't know how to hold other variables constant, and that's also an area of active research. But you can see it looks basically the same plus the balcony, which is pretty cool. Oh. So there's before, and there's after. And this is a live demo. If you search for Pix-to-Pix online, it's a live demo. You can go through and modify the building yourself. And sometimes the results are better than others, but they're mostly surprisingly good. So this is not going to replace architects, but you can imagine it being a tool that people would use. Now, there's also other things you can apply it to. So this same website has examples of applying it to pictures of cats. You draw a line drawing of a cat, and it makes a more or less photorealistic picture of a cat in whatever pose you drew. Or what's really cool, especially to the designers in here, is there's an example where you draw a line drawing of a handbag, and it creates a more or less photorealistic photo of a handbag. So you can imagine this as a fashion designer tweaking a dress or a handbag or some other item and seeing what it might actually look like without having to go through and do more expensive, time-consuming renders or actually building something. So again, this is something that really exists that you can go out and try today. So in our example here of selling ebooks, a generative adversarial network might allow us to take a book title, user-submitted book title, and generate some basic cover. I mean, we're not really there yet, but you can imagine this technology getting good enough in the next few years that you could actually do that. So next thing I want to talk about is a recurrent neural network. So everything I've talked about until now has been more or less mapping inputs to outputs. You have a picture, it's a dog. You have a face, it's this person. Recurrent neural networks act on sequences, and that's either sequences of characters, sequences of text, or audio over time, so speech, or whether it's speech recognition or translation or analysis. And it has this concept of this happened after this. This happened in some relation to some other piece of data. So for example here, we trained a neural network on the input of all of Shakespeare's plays. So this takes just all the open source text from all of Shakespeare. Didn't teach it anything about English. We just gave it all the characters in a row. And this is what it popped out. It's not exactly sensible, but then again, what part of Shakespeare is? It looks more or less right. You got the right syntax. You have the people, the person's name, colon, some stuff they said in English-ish. It more or less works on a small scale. Now, what doesn't work is you generate, a play's length of this. It's not going to pop out with something that actually makes sense with a plot and anything that follows any sort of sensible storyline. And that's really where a lot of the issues with machine learning still are, is they're really good at making things look like what you want, but they're not necessarily good at understanding it. It doesn't know that it's writing a play, that there's any concept called plot. All it knows is that it's trying to output text that looks similar to some other text. And if we try this again, you can do this a lot of different things. Some of it's kind of fun. Here we took the Linux kernel source code in C++, and we had it just output some C++. And what's interesting about this is it's more or less syntactically correct. It doesn't do anything useful. I mean, it uses variables that aren't defined and all that, but it's got multi-line comments. It's got definitions of methods. It has more or less correct syntax. So you can imagine an area of research as we move forward is having stuff that can generate things that look right but actually mean something on a larger sense. So I want to kind of show you just real quick how recurrent neural networks work kind of on a technical level. And you can think of them kind of like convolutional neural networks, where they have different layers that kind of add up and higher layers of abstraction. So the lowest layers, like on a convolutional network, you had pixels, and then you moved up onto features like eyes, then you moved up onto faces. With recurrent neural networks, you might think of lower levels like things that are character specific, and then higher levels being state that means something. So in this example, I'm going to show you a recurrent neural network, an example that is in theory trained on a bunch of URLs. So this is my homepage, and I'm going to highlight a low-level concept, which is the idea of a slash. Slashes tend to happen after colons and after other slashes and after ends, because .com is a pretty common TLD. It's often followed by a slash. So we're going to say here that, okay, given HTTP colon, how likely is it that the next character is a slash? And this neuron gets really excited after it sees the colon, thinks it's a pretty good chance the next character is a slash. And then it is. And so then it sees one slash, and it's a 50-50 chance the next character might be a slash. It's less certain, but it is a slash. And then it sees one slash, and it's still a 50-50 chance the next character might be a slash, and so on. And then it goes, and you get to this point where you have COM, and it turns out COM is often followed by a slash. Now, it turns out my last name has COM in it, and I do have these unfortunate silent characters at the end. So this is always making my life difficult, especially doing machine learning. It thinks after the COM there's likely to be a slash. There is not. But the key here is that it gets it right more often than it gets it wrong. And it doesn't have to get it right 100% of the time, because there's higher levels of the network that will take the input from this, how much do I expect there to be a slash here, and combine it with other concepts within a URL and figure out how much to trust this input. So I'm going to show just one more brief example. It doesn't have to be on the character level. This is a slightly higher level concept of DNS. DNS isn't always, but often is 3 characters long. The part before the initial dot and then the top level domain is very often 3 characters long. So you might have a neuron here that gets really excited as it gets closer to 3 characters in. And then as, and even in the rogerpincombe.com, it gets excited there because it's a part of the DNS that is 3 characters in, even though it's not the right part. So again, you can imagine this being used by a higher level part of the network that understands if we're in the first part of the DNS in the subdomain, or if we're in the main part of the domain, and trusting the neuron based on that. So that's a brief overview, but the idea is that with recurrent neural networks, you're kind of understanding things at different levels over time rather than spatially with pixels. Recurrent neural networks are used a lot more than just on text. Again, you can use it on speech, translation, really anything with sequences. Spotify had a really cool blog article recently about how they are categorizing music genres based on using recurrent neural networks to actually analyze the audio itself. So for example, if there's a persistent bass line, then that means something about the genre and whether or not you might like it, which is kind of a cool use of it rather than just saying, oh, well, Joe likes this and I like this, so I might like other things that Joe likes, which is called collaborative filtering. So when it comes to our ebook example, recurrent neural networks are probably be used to, say, translate the book summary to Spanish or something along those lines. Or maybe generate an audiobook from this, which isn't that good yet, but it's interesting kind of how fast that's progressing. One last type of machine learning I'd like to talk about is reinforcement learning. Now, everything I've talked about up until now has been taking input data and getting output data. Reinforcement learning is a little bit different. So if you've heard of Google's big AlphaGo competition, or any of the work that's been done to make Atari games playable by computers, that's all using reinforcement learning. And reinforcement learning, rather than having a problem input and an expected output, it actually has an agent, and you train the agent. So think of the agent almost like a living thing. It has to make decisions, it has to plan and figure out what the appropriate, what to do to get the outcome it wants. So, but it's not quite that simple. There's actually two separate problems that reinforcement learning has to handle in tandem. The first one is that it has to learn how its actions affect the state of the world. So for example, if Mario stays right there, there's a 10% chance that he's going to die just from hitting the time limit. And there's a 90% chance that his score stays 0 and nothing particularly bad happens. If he moves right, there's a 95% chance his score goes up. And there's a 5% chance that he hits an enemy and dies. And if he jumps, there's a 5% chance that he kills an enemy and his score goes up, and there's a 90% chance that his score stays 0. So that's basically the estimate of how does his actions affect the state of the world. But now that he knows that those are the things he can do and what is likely the outcome, he now has to figure out how to actually act. Because if you look at these, if he just moves right, that's the smartest move, because his score goes up 95% of the time. So you should just always move right, and then eventually he'll die. So what we want to do is we want to have some sort of sense of longer-term planning, of being able to select a series of actions or a series of state changes that are actually beneficial in the long term. And this is something I'm not going to get into too much more of the technical details, but it's a really interesting area of research, and it's kind of a whole separate branch from the rest of machine learning in terms of what it's being applied to. So again, you sometimes come up with interesting situations like if he stays right there, he has the best chance of a high score because he might fall on the enemy. But if he miscalculated exactly where he's falling, he also has a higher chance of dying if he stays there. But if he moves right, he has a higher chance of survival, but his score is not as likely to be as high. So what is the actual thing you're trying to optimize for? You have to manually specify, the carrot and the stick. You have to say, what is it that we care about? What is the outcome we want? So in this example of ebook marketplace, reinforcement learning doesn't directly fit in as clearly, but you can imagine creating some sort of simulation of different companies in the marketplace and saying, how would it play out if we partner with Amazon versus we directly compete with Amazon? And there's actually some work being done in government and in government contractors where they're trying to actually create these models of how different countries interact and how different entities play out in certain scenarios. It's definitely an area of active research. So I want to talk about a couple more things. We've gone through all the major types of machine learning that are relevant at the moment, but I wanted to talk about, do you really need big data? So originally this conference was going to be about privacy as well, and when you hear machine learning, you hear big data is necessary. And the reason for that, as we described earlier, when you have really complex models, when you have really deep networks, there's a lot of those parameters you're trying to optimize. It's not just slope and y-intercept, it's tens of thousands, maybe even hundreds of thousands of parameters you need to find the exact right value for. So the more data samples you have, the more likely you are to get an accurate parameters. But there's ways around that. There's ways to do better even if you don't have large data. So for example, one really interesting thing that's been done recently is using convolutional neural networks to diagnose cancer in tissues. So if you take biopsies of tissues and you tell the network that this one is cancer, this one's not cancer, it eventually gets reasonably good at figuring out, just from a photo, is there cancer in this tissue or not? But it's not perfect because there's just not a huge sample size of tissues with cancer, at least ones that have been prepared for the machine learning inputs. But what ends up happening is if you first train the neural network on just a standard Google ImageNet training set, so pictures of dogs, pictures of people, pictures of cats, things that aren't relevant for diagnosing cancer, but you train it on that first, and then after that you train the same network on the cancer, then you get much more accurate results. And the reason for that is even though a dog or a person's face isn't relevant in these images, the lower levels, remember the things like dots and edges and things that make up features in images, those things do kind of transfer over. And having these structures in place, the connections within the network in order to identify those things helps it much more quickly learn how to use those same features to identify things like cancer or other things you might be trying to analyze. So you can do the same thing with, let's say you have some other type of image you're trying to categorize that might not be standard. So something that isn't in a Google image set, but you still want to be able to differentiate between a picture of this particular breed of dog and a picture of this other particular breed of dog that you're breeding at your, and so if you start with the basic ImageNet network and then you do some additional training, you get much better results. And this actually, with the tissue cancer screening, tends to get better results than human. So doctors using this can be more accurate than just a trained eye doctor. So I wanted to leave you with one last example. A friend of mine at Georgia Tech, Tiffany Zhang, made this really silly startup generator. And what it is it's a site that just generates landing pages for fake companies. And some of them are actually fairly convincing. You go to one of these without any context, and it takes you a second to realize it's not real. Now, I've cherry-picked a few of the best examples here. I went through a whole bunch of examples and picked the ones that I thought were most realistic. Now, the thing is, if I did that as a human, maybe we can train computers to do that. Because one of the things that a lot of this machine learning comes down to is if you ever have an intuition about something, about, oh, this feels right, it's not just some abstract intuition. What it is you've seen enough of this data. You have enough context to understand it. So let's say you're a realtor and you're selling houses, and you look at a house and you know about how much that house is worth and maybe the kind of person who might be into buying that house. And that's because you've sold a lot of houses. So for machine learning, you're basically trying to do the same thing. You're trying to quantify that intuition. So if we look at these two pages and we say, well, the one on the right looks a little more realistic. I believe that's a real thing more. Maybe there's a way that we can teach machine learning to figure that out as well. So in this case, you might, your user will go to the site, they'll keep clicking to refresh until they come up with a site that looks good, and then they'll share that one. So that's an input. The fact that they shared one and they skipped the other ones, you can feed in as training data and say, okay, well, something about this one that they shared is better. And the machine learning, if you have enough data, is good at actually going through and figuring out, okay, well, what about it is better? Given all the things we know about what's different, where are the actual patterns? So it can't design a website for you, but it can probably tweak it. Think of combining this with A/B testing or multivariate testing to have some sense of what the best combination of features or variations on your site could be, especially with different user groups. So I want to just, in summary, remind you that machine learning is task-specific, narrow AI. This is not consciousness. It's nothing super scary and fancy. It's just math equations. And the process for solving the math equations. And my computer's still on. Nope, hold on. Let me unplug. No, it still looks good on here. Hold on one second. Let me put presenter mode, extend. Hold on, I'm just going to switch it back here, 1 second. Or not. Here, let me do this on from current slide, and we want to go back. There we go. Okay, so in summary, you've got, it's just math. You're just solving math. But you don't even need to understand the math, because there are plenty of systems out there that do the hard work for you. We're at a point with machine learning where you really just kind of need to plug and play. And as long as you're not doing cutting-edge research, there's a lot of cool stuff you can do with just existing systems and APIs. And it's just a matter of kind of figuring out what problem you're trying to solve and what type of machine learning can help solve that for you. So again, there's different kinds of algorithms, and they're all good at solving specific things. So I hope I gave you a good overview of the kinds of problems machine learning can solve. So when you see something that you're trying to solve, you have an idea of what path to go down. Also, big data is helpful, but you might not need it. Try and find a problem that's similar that you can jumpstart off of their results, so you don't need to start from the ground up. And don't be afraid of computers replacing designers, but get creative and use machine learning as a tool to enhance your productivity. So again, my name is Roger Pincombe. You can find more about me at rogerpincombe.com or email me at roger@pincombe.com. And I'm OKGoDoIt on Twitter. And one last thing, I was putting a photo of myself in here in case anyone was watching the screencast and didn't actually know what I looked like. And as I pasted it in there, PowerPoint popped up with suggested alt text. And I thought this was kind of cool, because this is a real-world use case of machine learning that your average person might not have, they don't care how it's implemented, but it provides real value. It says a person wearing a suit and tie. Now, it's not perfect. I'm not wearing a tie in there, but it gets the point across. And the point is, it helps people that are blind know what's going on in the presentation, and I didn't have to do anything. Some designer at Microsoft said, hey, what if we did this automatically for people? You hook it up to an existing backend. There are plenty of APIs that'll do this for you. And now you have this extra nice little surprise feature that I don't have to put any effort into. So as designers, think about what parts of your job or your product or whatever you're building can maybe be automated a little bit, or that you can make that much smarter or that much easier for users by using some form of machine learning. Thank you. Well, I'll just repeat the question.
Yeah, I was kind of stuck on one thing in the beginning. I was wondering, how does the information get back to the neural network as an affirmative choice? Like, how does it know? How does that? I was just wondering what that looks like. Is it another equation?
Yeah, I kind of glossed over the mechanics of it, but let's say on the level of you're using a library. So let's say you're using some sort of TensorFlow library. You would pass in the actual data. You'd pass in a list of the inputs and the expected output for each item. So you might have a row that is button size 200, price 50, and reviews 2, and then you expect the value to be 50. And so there's two steps. There's the training, where you give it all the initial data, and it creates a model that finds those parameters. And then once you have a trained model, you would then go through and, using whatever framework you're using, you'd say, okay, take this model, here's the actual data I want an estimate on. I want a prediction on what you think the output value should be. What do you think the price, or how many people do you think will buy this book? And so usually there's some sort of function where you basically give it the input and it pops out with the output, and that would be in line with whatever you trained it on. Does that answer your question?
Kind of, not exactly. Just how does it know then? How does it get positive reinforcement? Like, what is learning, for it to take that information? I don't know if that question makes sense.
So the question, I think what you're saying is, how does it take into account whether or not its answer was correct?
Yes, exactly.
So that's actually a type of learning called online learning. So generally, actually, the easiest way to do machine learning is you don't do that. You take existing data that you know the answer to, you train it on it, it generates a model, and then you use that model to output things. And if your output's wrong, you don't necessarily take that into account, but maybe you record that. So later at some point during some batch process, you retrain the model with the new data. Now, there's a different type of learning or different way of training that's called online learning, and that's basically where every time you get a result, you're updating the model. It's a little harder to do computationally because if you have batch training, so that's when you take everything and you train it all at once, you can offload it onto a graphics card and you can do it in ways that are more efficient. Online learning, you can do that, but it's a little trickier in practice.
Sorry, whoever wants to ask questions, I can pass the mic for you so that everyone can hear your question.
Okay.
Right.
What is inferencing?
So inferencing, inference is basically that's basically the term for when you're predicting. I believe it is possible. I'm mixing that up, but I believe so. When you train the model, you come up with a trained model that you then use to make an inference or a guess about, given an input, what the output should be. Don't quote me on that, but a prediction is the term I would use for that. So, but I believe that's also called inferencing. Anyone else? Cool. I believe she's going to be making the slides available along with the video on the website. So if there is anything you wanted to go back and check out, feel free to check it out on there. And also, I'm OK Go Do It on Twitter. Thank you.